Hello everyone. Today we are going to learn X-ray diffraction. This is an important technique in nanomaterial characterization. In today's lecture, we are going to learn the working principle of XRD, Bragg's law and applications of XRD. At the end of the lecture, we will also have a practical demonstration to understand this technique more in detail. Let us see what is X-ray diffraction. X-ray diffraction, that is XRD, is a non-destructive analytical technique used to analyze physical properties such as phase composition, crystal structure and orientation of powder, solid and liquid samples. It can analyze all kinds of amorphous powder and crystalline materials. It is ideal for probing the interplanar distance in the crystalline materials. Interplanar distance means it is the distance between any two parallel planes in the crystal. XRD can also distinguish between crystalline and amorphous phases as well as the different crystal polymorphs. And XRD provides data regarding crystal structure, phase identification, lattice parameters and crystallite size and strain. Let us briefly see the history of XRD. X-ray was discovered in 1895 and for the discovery of X-ray the Nobel Prize was given in 1901. Followed by the discovery of X-ray, so the X-ray diffraction was discovered in 1912 and Nobel Prize was given in 1914. So based on the X-ray diffraction you can see that there are so many Nobel Prize. So which shows the importance of this technique, including the structure of DNA which was illustrated using this XRD and protein structure. So this technique played a very important role in the not only in the material characterization, it also played a very important role in the biological science. Let us see what is X-rays. X-rays are electromagnetic radiation with the wavelength in the range of 0.01 to 10 nanometer. And these X-rays possess high energy and are capable of penetrating most of the materials. And you can see this is the first X-ray apparatus used by Röntgen in 1895 while experimenting with the cathode rays, and these X-rays can exhibit absorption, scattering and diffraction upon interaction with the matter. Let us see how these X-rays are generated. So these X-rays are generated by striking accelerating electrons onto an anodic metal target coming from cathode metal under a closed vacuum, and this anode is mainly made up of copper or molybdenum. And if you see that the electrons emitted from the heated cathode, that is a tungsten filament, through the thermionic emission, and this will be accelerated through the high voltage towards the anode. Upon striking the anode, the high energy electrons interact with atoms producing X-rays through two main processes. One is Bremsstrahlung radiation, the other one is characteristic radiation. So this Bremsstrahlung radiation is also known as braking radiation. It is a type of electromagnetic radiation that occurs when a charged particle like electron slows down or is deflected when it interacts with the matter. So you can see here the target nuclei, it is slowing down on the oncoming electrons and which release their energy as X-rays. So it occurs when fast moving electrons are decelerated by the electric field of atomic nuclei, converting their kinetic energy into X-ray photons while conserving the energy. The next one is characteristic radiation. Here you can see the inertial electrons of the metal target are knocked out by the incident electrons beam, then the vacancy is filled by a higher energy electron and the energy released is emitted as X-rays. From this picture we can understand how these X-rays are generated. So as I told earlier, these X-rays are generated when high energy electrons from a heated cathode strike a metal anode, that is a target, and here due to the rapid deceleration of electrons near the nucleus of the target atom which produce the Bremsstrahlung radiation, that is a continuous spectrum. Additionally, when these high energy electrons are ejected, the inertial electrons from the target atoms, what happens, these outer shell electrons fill these vacancies and releasing an extra energy as characteristic radiation which will have a discrete wavelength. So both types of radiations like Bremsstrahlung radiation as well as the characteristic radiation combine to form the X-ray. Let us see the geometry of crystals. A crystal structure refers to the organized arrangement of atoms, ions or molecules in a crystalline material. In a crystal, the components are arranged in a repeating pattern that extends in all three spatial dimensions, forming a lattice. So this is a unit cell. So each point in the lattice represents the position of a particle. It can be atom or ion or molecule. The smallest repeating structure of the crystal lattice is called as unit cell. And the dimension of unit cell includes the length of the edges, that is the ABC, and their angle is alpha, beta and gamma of the unit cell. And these lattice parameters can be determined by XRD, which can be further used to identify the crystal structure. So, this unit cell is like a kind of bricks. By using that, for example, we are using the bricks to construct the home of different designs, and for the crystal structure this unit cell arrangement is very important. So, we have different kind of crystals. So, this crystal structure can be studied or determined by the XRD, and also we can understand the lattice parameters using this XRD. Let us see what is Miller indices. Dr. Miller devised this mathematical system for describing any crystal phase or group of similar forms. And these Miller indices are set of 3 numbers, that is HKL, used to describe the orientation of crystal plane or set of parallel planes within a crystal lattice. And these Miller indices are determined by first identifying the points where the plane intersect each axis. Each number is then reciprocated and converted into a whole number. So, this I will explain in the next slide in detail. So, let us see the significance of these Miller indices. So, this Miller index is useful for identifying the specific planes or direction in the crystal lattice, and also it will be helpful for understanding the properties of materials. For example, we can identify the different planes in a crystal which may be related to different physical properties of a material. It can be relevant to electrical conductivity or it may be relevant to the hardness of the material. And these are the various examples of the Miller indices, and we are going to take an example of this one 100, how we get this 100 by this Miller indices. So, let us see an example to understand the Miller indices. So, in this case let us take a cubic unit cell of equal edge length, that is A. The first step is to determine the intercept. So, identify the location where the plane intercepts the x, y and z axis. Once the plane cuts exactly at A 00, and since it is a parallel to y and z axis, the respective intercepts will be infinity. So, that is why the intercept for the x, y and z axis is A, infinity and infinity. So, the next step is convert to fractional coordinates. So, now we will convert them into fractional coordinates by dividing each of them by respective edge length. Since it is a cubic lattice, each edge length is the same. So, we will divide each of them by A. So, here the fractional coordinates for x, y, z intercept become A by A, infinity by A and infinity by A, which equals to 1, infinity and infinity. Then third step is that take the reciprocals. So, the final step is to take the reciprocal of each coordinate and convert them to the whole numbers. So, the reciprocal of 1, infinity and infinity will be 1 by 1, 1 by infinity and 1 by infinity, which is equal to 1, 0, 0. So, the Miller indices for these planes become 1, 0, 0. Let us see what is diffraction. Diffraction is a phenomenon where waves such as light, sound or X-rays bend around obstacles or spread out after passing through a narrow openings or slits. This occurs when the wave interacts with the structures or objects that have dimensions comparable to its wavelength, resulting in constructive or destructive interference. The atomic planes in the crystal act like a set of closely spaced slits, causing the X-rays to diffract. So, if we take a crystal, these atomic planes in the crystal, it act like a slits. So, it makes the X-ray to diffract. And let us see what is constructive interference and destructive interference. So, the constructive interference means the waves in the same phase leads to peak in the diffraction pattern. We can see the waves are in the same phase. So, we will get the peak. And while out of phase waves undergo destructive interference and it will cancel out each other. You can see here the waves are is out of phase. So, due to which it will cancel out each other, and that is called destructive interference. And from this picture you can see this red color ring. So, the red color ring is the constructive interference and the black color one is the destructive interference. So, whatever we are getting this red color ring, this is the constructive interference, and where you are not seeing the red color ring, that is the black color one, that is the destructive interference. Let us see what is Bragg's law. Bragg's law explains the condition for constructive interference of X-rays scattered by a crystal lattice, it relates the X-ray wavelength to the interplanar spacing in the crystal and the angle of incidence. So, Brake's law states that n lambda equal to 2d sin theta, where n is the order of diffraction and the lambda is the wavelength of X-ray and d is the interplanar spacing, that is the distance between the crystal plane, and theta is the angle between the incident X-ray beam and the crystal plane. Let us see the parts of XRD. The first one is the X-ray source, which produces the X-rays typically using a vacuum sealed tube, and commonly used metals are copper and molybdenum targets for characteristic X-rays. Then we have these monochromator, and monochromator filters unwanted wavelength and isolating a single wavelength for precise diffraction analysis. And we have this sample holder. So, it securely holds the sample in place and ensures the correct alignment for interaction with the X-rays. Then we have this goniometer. So, this is a mechanical device that precisely positions the sample, detector and the X-ray source at specific angles. And we have the collimator, and this ensures that the X-ray beam is narrow and well aligned, reducing the divergence to produce a parallel beam for accurate diffraction measurement. Then we have the detector, which measures the intensity of the diffracted X-rays, and the common types include scintillation counters and the CCD detectors. Then finally, we have the data processing unit, that is a computer with the software for recording and processing and analyzing the diffraction patterns. Let us see how diffractometer works. So, here the X-rays are produced by bombarding the high energy electrons onto a metal anode, that is we can use a copper or molybdenum as I told earlier. So, the sample is mounted on a holder and aligned precisely. Then a collimated X-ray beam is directed onto the sample. Then the X-rays interact with the crystal lattice, producing a diffracted beams based on the Brake's law. And the diffracted X-rays are detected by a rotating detector at various angles. The intensity of the diffracted X-rays is recorded as a function of the angle. Then the diffraction pattern is analyzed to determine the material's crystal structure, phase and other properties. So, from this slide you can understand how the crystal polymorphs can be identified by XRD. You can see these, the quartz, cristobalite and amorphous SiO2 all are made up of SiO2, but produce different diffraction patterns because of different periodicity and arrangement of atoms in the material. From this picture you can understand this SiO2, it is amorphous in nature, so there is no peaks, whereas in case of quartz and cristobalite you can see the peak, but the position of peak is different. So, based on that we can identify the polymorphs of the crystal. Let us see another example for understanding the X-ray diffraction pattern. So, here we are going to compare the graphene oxide and the reduced graphene oxide. In case of graphene oxide, you are able to get the peak around 11.01 and the plane is 001, but this peak is diminished after reduction. In the reduced graphene oxide you are not able to see this particular peak, and but there is a new peak at around 26.8 and the plane is 002. So, the increased interplanar spacing in the graphene oxide is due to the intercalation of the oxygen containing functional groups between the graphene layers, whereas in case of reduced graphene oxide it exhibits an interplanar spacing similar to the graphite. So, which indicates that the reduction process decreases the interlayer distance by removing these functional groups. Let us see the importance of proper sample preparation, and this is an example of ideal powder sample preparation, and here you can see the complete rings corresponds to an ideal powder sample with large number of small randomly oriented crystallites. So, you will get the small and randomly oriented crystallites, and this ensures the diffraction contribution from all possible lattice planes. The measurement from this type of ideal sample can accurately represent the material's crystal structure, whereas in this case you can see here the sample are having small number large crystallites. The spotty or incomplete rings can be due to a sample with small number of large crystallites, and this incomplete representation of diffraction due to lower randomness of crystallite arrangements. So, this is not an ideal measurement and cannot be relied upon to accurately determine the crystal structure. So, that is why a finely ground powder sample gives a better diffraction pattern. So, the sample preparation is very important in the XRD. Let us see some of the applications of XRD. In material science, XRD will be useful for understanding the crystal structure as well as the phase identification. In nanotechnology, we can use it for nanoparticles size estimation, lattice strain analysis, and characterization of nanocomposites and thin films. In pharmaceutical industries, it will be useful for understanding the drug polymorphs, crystallinity, and stability to optimize the bioavailability. For example, the different crystalline forms will have a different solubility as well as the absorption. So, based on that, we can understand their bioavailability. And in case of geology and mineralogy, it will be useful for identification of minerals and soil composition and crystal phases in the rocks. In environmental science, it will be useful for analyzing the soil and pollutants and particulate matter in the atmosphere. For example, it can be useful for detecting the toxic metal oxide in the soil samples. In case of forensic science, so it will be useful for examination of materials like paints, pigments, and also for identifying the unknown substances. Let us see an example for understanding how this XRD can be useful for identification of these gold nanoparticles. And you can see there are 4 prominent diffraction peaks for the gold nanoparticle, and this is mainly the reflections of the face centered cubic of gold metal nanoparticles. And this indicates that the synthesized tannic acid capped gold nanoparticle comprises the pure crystalline gold, and this can be compared with the standard, that is the JCPDS, that is the Joint Committee on Powder Diffraction Standard. We can compare with this standard and we can confirm the gold nanoparticle. The intensity of the peak that corresponds to this triple one, you can see this peak is intensity is very high. So, when compared to the other 3 peaks, so that indicates that, so this is the plane which is the predominant orientation for growth of the nanoparticles. Let us see some of the problems what we face when you do the XRD and how to overcome those challenges. So, the first problem is weak or no diffraction peaks. So, the reason may be the sample is not properly aligned. So, recheck the sample alignment, and it may be due to the insufficient sample quantity. So, increase the amount of sample or ensure uniform distribution. And the next problem is broad diffraction peaks. It may be due to the poor crystallinity or small crystallites. So, prepare a better crystallized sample, and it may be also due to the instrumental broadening. Perform calibration using a standard sample. And if you are facing like a overlapping of peaks, so that is due to the multiple phases or complex structure, use advanced data analysis tools or complementary techniques like Rietveld refinement. And if you are getting the background noise in pattern, it may be due to the contaminants in the sample. So, clean the sample holder and ensure no external materials interfere. And if you are getting the peak shifts, that may be due to the misalignment of the sample or instrument. So, realign the sample and recalibrate the instrument, or it may be due to the residual stress or strain. So, you have to check it whether is there any account for these effects during the analysis. And if you are getting the low resolution, it may be due to the incorrect scan speed. Use a slower scan speed for better peak resolution. And if you are getting the unstable intensity or fluctuation, so that may be due to the old X-ray tube or unstable power supply. Replace the X-ray tube and ensure stable power supply. So, if the data is not reproducible, it may be due to the inconsistent sample preparation. Ensure uniform thickness and density of sample, and also it may be due to the temperature or humidity variation. So, always perform the analysis in a controlled environment. Hope you got the overall idea about the XRD. Let us go to the lab and learn this technique more in detail. Today we are going to do XRD analysis of powdered graphene oxide. For this, we require a sample holder. The sample is kept in the center cavity of the holder. The powdered sample should be properly leveled to get good diffraction of the X-rays from the sample. For this purpose, we use a clean glass slide with which we can level the sample in the holder. Additionally, we will need a spatula, tissue paper, beaker to discard the waste, and isopropanol for cleaning. We cannot use solvents like acetone for cleaning as it can damage the sample holder. First, using tissue paper and isopropanol, we will clean the spatula to get rid of any residual material from the spatula. Then we will wipe the center cavity of the sample holder with isopropanol. Using the clean spatula, we will completely fill the center cavity with our desired sample. Next, we will wipe the glass slide as well with the isopropanol, which we will use to level the sample in the holder. Place the glass slide on the holder and ensure that the sample cavity is completely filled and there is no space between the sample and the glass slide. This is Bruker D8 Advanced XRD machine, which we will use for our analysis. First, turn on the machine. Let us briefly learn the instrumentation part. This is the X-ray source which generates the X-rays for analysis. Next is the collimator, which narrows down the beam of X-ray, which is then passed through a shutter and a slit to focus the X-rays onto the sample. The instrument also has an anti-scatter screen with a knife edge at the end to block the stray X-rays. And we have the sample stage where the sample is kept. The system is coupled with a goniometer that can independently move the source and detector and control the angle of incidence of the X-rays beam onto the sample. On the other side, we have another collimator and slit setup which focus the X-rays that are reflected from the sample onto the detector, and finally the detector detects the reflected X-rays to generate the data. This machine is paired with a robotic sampling system which can automatically load and unload the samples. We can place up to 15 samples in one holder, and there are total of 6 holders, so we can analyze 90 samples at a time in this machine. We can keep the sample in any of these sample positions, which we have to specify in the control software. We have prepared the sample. You can see that the sample is filled in the center cavity of the sample holder. We are placing our sample in the A10 position of the holder, according to which we will give the command to the automatic sampler. Close the machine door and then turn on the machine. You can see that X-rays are switched on, which is indicated by the indicator lights, but these X-rays will not pass on to the sample because the shutter is still closed, which we will open only on giving the start command. After the X-rays are turned on, the door will not open to protect the user from X-ray radiation. This is the commander software that controls the operation of the XRD machine. Here you can see that the X-ray source is on and the shutter is closed till the process starts. First, we need to set the voltage and the current for the X-ray source. We will set the voltage and current to 40 kilowatt and 40 milliampere respectively by increasing the voltage and current values alternatively with increments of 5 units at a time to prevent damage to the X-ray source. Once the voltage and current values are set, we will give the command to insert the sample onto the sample stage. You can see that the robotic arm takes the sample from the instructed A10 sample position and keeps it in the sample stage. On the right hand side, we have the setup of the analysis parameters where the scan type has been set to coupled to theta or theta setting. The source and detector will move simultaneously. The time taken for measurement at each step has been set to 0.1 seconds. The total steps according to the 2 theta values are around 4600 and it will take around 475 seconds to complete the measurement. The 2 theta values of our measurement have been set from a start position of 5 degrees to a stop position at 100 degrees with an increment of 0.02 degrees at each step. After setting the parameters, we can move on to the measurement. Once we press start, the source and the detector will move to the starting 2 theta position, which we have set at 5 degrees. You can see that after starting the measurement, the shutter has opened, which means that the X-rays are falling on the sample and going to the detector. The machine has started the measurements and the diffractions are being displayed in the form of peaks. After process completion, we will unload the sample by clicking the sample unload button. The robotic hand automatically takes the sample and place it in the initial place. After this, we have to decrease the voltage and current to their initial values. Now switch off the X-rays using the X-ray toggle button. Now we can safely open the door of the machine and take out the sample. Close the door and switch off the machine. From this data, you can understand the diffraction peak at 10.67 and the reflection plane 001 confirmed the characteristic peak of graphene oxide. As a summary, in today's lecture, we learned the basics of X-rays and diffraction, and we also learned the principle of XRD and applications of XRD. Also, through practical demonstration, we learned this XRD more in detail. Thank you for your kind attention. I will see you in another interesting lecture.